Greetings everyone and welcome back to the bench. Today we're going to talk about damping factor and how it applies to audio amplifiers and speakers. It's one of those terms that kind of get pushed a little bit in some of the marketing, and we'll talk about that. You know, amplifiers tend to be rated in very high damping factor figures, and that is true. There's no issue there. But it's how much damping factor you actually need is the issue. You know, you'll see amplifiers with damping factors over 1,000. And is that really necessary? And in a practical sense, is that even achievable, you know, for the loudspeaker to see that much damping factor? So we'll look at that, and we'll do some experiments. We'll play around with some loudspeakers, and we'll also measure damping factor with some amplifiers. You'll see the damping factor figure on the specifications of audio receivers and power amplifiers and things like that. You don't see them very often. I haven't seen any on these little boards and kits that I review on my channel, but here's an example of a Kenwood receiver. You can see down here they're giving the damping factor of 50 at 8 ohms. So what is damping factor? Well, it's a ratio. It's a dimensionless number, and like I say, it's a ratio of the load impedance to the amplifier's internal impedance, or I'm showing here with these resistors. So it's R load to R source. So why are we worried about damping factor in the first place? Well, it all hinges on the loudspeaker. And I have a small speaker here to use as a demonstrator. What it has is a magnet, and there's a round slot inside this magnet where a coil sits. That slot has a very high concentrated magnetic flux. And if we put a signal on that coil, it'll make the speaker cone move because it is connected to that coil of wire. Now, something interesting happens if I just push on this cone. It'll make that coil move in the magnetic field and produce a voltage. And why I mentioned this will become apparent momentarily. When the speaker is playing music, for example, and say a musical note is playing and it suddenly stops, this cone will want to return to a home position. It has a suspension around the outside, and that brown suspension down by the coil called the spider, and it returns the speaker to a home position. Well, because it has some springiness to it, it's going to want to continue to vibrate at a natural frequency after the signal is removed to return it to its home position. And it overshoots a little bit and oscillates, but it does continue to oscillate after the signal is removed. Now, like I mentioned before, that movement is going to produce voltage at the terminals, and if we short that out, it's going to resist that movement. It's going to dampen that motion and reduce that effect, which could color the sound. And of course, we don't want the speaker to color the sound of our music, so we certainly want to damp out those oscillations if we can. Okay, so I have this loudspeaker. It's a 12-inch PA type. I'm not sure what it is, a mid-bass driver, maybe even a guitar type speaker. It's got a pretty massive magnet on it. So what I'll do is I'll tap the cone. I use a pencil eraser because if I use my finger and I don't pull it off quick enough, it will affect the results. So I have my scope set up. I have it set for a single shot trigger. So I'll set the camera here and I'll tap the cone. And look at that. Made a waveform. Let me turn that down and oops, I dropped the pencil. So it made this waveform. It went on for 1, 2, 3, 4, probably 5 or 6 cycles. You can see it a little bit here, but it's pretty well damped out by then. So yeah, you can see that the speaker does oscillate. You know, it kind of overshoots, and then as energy is absorbed, it will finally dampen out. Okay, so now I've connected this resistor here. It's an 8 ohm load, so it represents a damping factor of 1 because the speaker is also an 8 ohm nominal impedance. Well, I accidentally dropped this on the floor and must have stepped on it or something because the ceramic shell has broken off, but it still works fine. Now, because we are putting a load on the output, it's going to lower this signal somewhat, so I will compensate, but we should see that these oscillations are more damped. So let me trigger the scope. There we go. So yeah, I need to turn that up. I'll try it again. There you go. So here's the initial pulse, and the pencil pushes the cone down, makes the waveform, and then look what happens here. It's damped out, so the return is much weaker, but look at this, there is no oscillation at all, just that one event, and it's pretty well damped. Even with a damping factor of 1, it pretty much has taken care of it. Okay, so what about a speaker that is in an enclosure? Let's see how that responds. Okay, I don't have a lot of room for it, but I have this 8-inch subwoofer in an enclosure that's ported, and I will see how that responds. It is also 8 ohm loads, but I don't have any resistor connected to it right now. So tap the cone and see what we get there. So I can turn that up a little, I guess. Let's re-trigger that. Now that's interesting. We got this weird 3-stepping wave. The waveform starts going down. I must have had the polarity reversed on the other speaker, but yeah, this is the initial impact of the eraser pushing the cone down. And yeah, it's more of a complex wave, and it does go on for a little while. I think that has to do with the porting. The box is tuned to a certain frequency, and the speaker driver itself has its own frequency, so perhaps that interplay is causing that more complex waveform. Let me cover the port and see what happens. Okay, I covered the port. Let me do that again. I kind of bounced the eraser. Yeah, that's more like it. Yeah, it does oscillate. Let's try that again. Yep, pretty much repeatable. So again, I will connect that resistor up and see what the result is. Okay, I've hooked up the 8 ohm load to the output, and I'll tap it. So yeah, we're getting that weird double humped wave again. Let me cover up the port and see what it does. Okay, so it does dampen it, but not as good as before with the other speaker. See, it does go on for a smaller but a second oscillation. Let me try it one more time. Oops, I double bounced. Double bounced again. There we go. Yeah, Probably not a perfect hit there. There we go, that's better. Yeah, it is damping it out pretty good, but a little small wave after that. But you can see just having a damping factor of 1, in other words, the impedance of the loudspeaker versus the impedance of the resistor. Of course, the impedance of the loudspeaker will change at different frequencies because it is an impedance, it's not a pure resistance. Okay, so now I'll measure the output impedance of a couple of amplifiers. I'm glad I kept this one on the breadboard. This is actually a headphone amplifier, and we'll do a couple experiments on that. Made a video on this several months ago. Really impressed with its performance. And this is a TDA 2050, and we'll measure its output impedance. Okay, so I have the headphone amplifier hooked up, and here is a schematic of one channel of that amplifier. Notice the output transistors. The output connection here is linked through 10 ohm resistors. So the upper half of the sine wave is handled by the upper transistor, the lower half of the sine wave, the lower transistor. So there's always that 10 ohm resistor in series with the output. So would the output impedance be 10 ohms? Well, not exactly. And I'll show you why. So being a headphone amplifier, it's not really designed for 8 ohm loads. So I'm going to use a 33 ohm resistor. So if you put that in series with the output, in other words, just connect it to the output to ground, the output node would become a voltage divider with these 10 ohm resistors and the 33 ohm resistor. And you should see it decrease. But will we? I don't know. Let's take a look. Okay, so I have a waveform. I'm measuring the output of this amplifier. I set it for 2 volts. 2 volts RMS. And that's no load. So there's no load right now. So let me connect the 33 ohm resistor. Okay. So this connects to the output, and this white gator clip links to the resistor, 33 ohms. Put the back of my finger on it. Yep, it is warming up. So it is acting as a load now. But it did not change. Still 2 volts. So the output impedance of this amplifier is, well, as I measured here, is 0. Now, if I had a more accurate meter, yeah, I could measure a small change. But it's not changing at all. 2.00 volts. So it's pretty safe to say that the output impedance of this headphone amplifier is extremely low. Okay, how in the heck could that be with 10 ohm resistors? Well, here's the magic. Notice this line going back through this 10K resistor back to the negative or the inverting terminal of the IC here. Well, this is negative feedback. And if there is any change on this output that differs from the input, negative feedback is going to fix that. It's going to change it. It's going to drive a higher voltage into these transistors. Or, well, you think of these devices as current amplifiers. So it's going to drive more current into these output transistors to correct that voltage drop we see. So to put it another way, with no load, you get the full output. When you put a load on it, it's going to cause a voltage divider situation here. You're going to lower that voltage. But negative feedback that's connected to the output node will detect that change and correct it. So negative feedback is the main determinant here in the amplifier's output impedance. So watch what happens. Now if I move this negative feedback node to this point before the output stage, we should now see a change. Let's try it. Okay, so now I move the negative feedback line that was connected to the output. So this line now connects to the output of the IC, but not the output from the power stage. So we have our 2 volts on the output, and I will connect the load, and look at that, it did change. It now dropped to 1.5 volts. So now I can calculate the output impedance of the amplifier in this state. Alright, so I calculated the output impedance of this amplifier the way I have it connected now with the feedback on the output of the IC instead of the final output stage. So what I've done is take the voltage drop across this resistor, divided it by the resistance itself. So 1.5 volts divided by 33 ohms gives us 45 milliamps. The change in voltage from when the output had no load on it to when the output had this load on it was 0.5 volts. So I take 0.5 volts divided by 45 milliamps. That gives me 11.1 ohms. That is the output impedance of this amplifier at 1 kilohertz. Of course, we can measure it at different frequencies. I don't suspect it would change very much. So connecting the negative feedback globally, in other words, encompassing the entire amplifier circuit, makes the output impedance very low, which would result in an extremely high damping factor. Like I said, it didn't change on the scope, so it's essentially infinite. But if I had a more sensitive meter or something, I could definitely detect a change and we could measure it. Now taking the negative feedback and putting it on the output here, in other words, leaving the output stage without negative feedback or global negative feedback, would make the output impedance much higher, 11.1 ohms. And that would result in a damping factor using 33 ohms as a load of about 3. Okay, so I've connected the TDA 2050 amplifier board up. Careful to measure with the scope right at the output terminals. If I measured at the load in this case, I'd be measuring voltage drop in these wires, and I don't want to do that because I want to see what the output impedance of this amplifier board alone is. And the load is not connected now, so it's just open load. Amplifier is running, and I set it for 10 volts RMS. So I will measure by connecting the load up to the output. Okay, now the load is connected and it didn't change. It's still 10 volts. So that tells me the output impedance of this amplifier is extremely low. And with the scope here, I cannot measure it. The damping factor would be infinite. Let's try another frequency. Okay, so now we're running at 20 hertz. I was running at 1 kilohertz before, by the way. Got it set at, well, about 10 volts. It's 9.99. Jumps around a little bit. So I will connect the 8 ohm load. And 9.98, 97, it jumps back and forth. Yeah, it's not really changing. Maybe 0.01. Okay, so I worked the calculation. With 9.99 volts across our 8 ohm load, it was putting 1.249 amps through that load. And we're getting a voltage drop of 0.001. So I take 0.001 divided by that current. The output impedance of the amp is 0.008 ohms, or 8 milliohms. So I take that ratio with our 8 ohm load divided by that 0.008, and the damping factor comes out to be 1000. Yep, 1000 from a cheap $3 chip amp. And again, at a higher frequency it was unmeasurable. So now let's try a frequency of 10,000 hertz. Okay, so now as you see we're at 10,000 hertz, 10 volts, no load. Now connect the 8 ohm resistor to the output, and it doesn't change one bit. Negative feedback is certainly a determinant in your output impedance, that's for sure. So yeah, I can't really measure it on the scope. It's above 1000, put it that way. So let me wrap this up in saying why a high damping factor is not necessary, even though solid state amplifiers with negative feedback are going to have a ton of damping factor, a very high value. In other words, low output impedance. Well, for one thing, the loudspeaker itself has a coil of wire, and even though it's a complex load, that coil of wire has an equivalent DC resistance. For example, an 8 ohm speaker will have about a 6 ohm series DC resistance, and that's going to be in series with the loudspeaker's impedance and the amplifier's output. So that's going to work against the damping factor figure. Of course, you have speaker wire. You know, if you have, say, 0.3 ohms of resistance in that speaker wire, you know, that's pretty significant. You know, the speaker wire alone, let's say 8 divided by 0.3, you know, that knocks your damping factor down to 26.6. So even if your amplifier did have a damping factor of 1000, that speaker wire alone just killed that. So there's two things. Now, one thing I should mention, that there are some loudspeakers that people say sound better with a low damping factor. In a 1 to 3 range, there are some loudspeakers that's supposed to sound better. I can't substantiate that myself. I've never tried it, but you know, perhaps it's true. Perhaps there are some speakers that sound better when they're working with a lower damping factor. Another thing I should mention as well, that there are designs of amplifiers that have high output resistance. In other words, the damping factor is low, and they can work great with those types of speakers that are said to sound better with a lower damping factor. And one last comment I sometimes hear is that, you know, that back EMF caused by the speaker puts that signal back into the amplifier's negative feedback loop and can change the sound. Well, that's bunk as well, because if the amplifier has extremely low output impedance like we measured here, it's just not going to make a difference. Well, I hope this sheds some light on output impedance of amplifiers and what damping factor is all about, and why it's not necessary that the damping factor is rated extremely high. You might have a tube amplifier with output transformers, and they tend not to have an extremely high damping factor. But it doesn't matter, because you don't need a high damping factor. Well, that's it. Thanks for watching.